Okay. All right, let's continue our ordinary differential equations. So we have started a new topic last time. You have actually an entire course that deals with ordinary differential equations. Here we will actually learn how can we solve them numerically. And every time I say that I'm discretizing an ODE or I'm solving it numerically, what I mean by that is that I'm finding solutions to whatever my function is that I'm looking for. I'm finding it at a discrete set of points as opposed to a formula, analytical formula that gives me solutions. So if I'm looking for a function f, it gives me f of x for whatever x I plug in. Okay. So the difference between numerical solutions is that they're essentially on a grid, they're discretized in some domain. Okay. And as a solution, I really get a vector if I'm in 1D, or an array if I'm in 2D, like two-dimensional array, which is a matrix. If I'm in 2D, three-dimensional array if I'm in 3D. Okay? So basically, I get a solution on discrete points in space. If I then, that's for instance an example right here. This picture here is actually from reservoir simulation. Okay? And I'm quite certain now, not quite certain what is plot here. It could be porosity, which is an input data, but it could be pressure or permeability or something that I solved for. Typically in reservoir simulation, I'm going to put in porosity and permeability as input, and what I'm going to get out is a set of pressures and velocities that I can plot. Okay. So this looks continuous, okay? But in reality, it's a grid. It's a grid just like as the data that you looked at in one of your first homeworks. You had to plot porosity and permeability, right? And you had a 100 by 60 by something matrix. Okay? So basically, if you had a numerical solution that was complementing the data, you would also have the same size, and you would have, for instance, pressure value on each point where you had porosity and permeability value. So basically, you would discretize that problem, and you would get solution only at those discrete points and not more than those. Now, data is visualized as very smooth because the data in between these discrete points is smoothed, it's interpolated. Okay. So I can come up with literally just like a line of data in between. So it can look really pretty, okay? But that doesn't mean that you have the data in an array. So basically, in between the points that you don't have, you can come up with what is plausible, okay, and what is close to the neighboring points. So it looks smooth, but it's actually computed on a grid. All right, so we had an example where basically I arrive at a differential equation of how the height changes in time for this tank. And part of the problem is that discharge rate from this tank actually depends on the height itself. So I have a differential equation that I have both time component comes in from the flux in that is time dependent. And then I also have, I depend on h itself on the other side. So essentially I have that dh dt is a function of both t and h itself. And that can or cannot, it's not always necessarily easy to analytically solve for such a problem, and that's where we can use numerical methods to solve. For instance, you could, in math, you would attack this with separation of variables or something of that sort. All right, so we have a differential equation. We will mostly deal with time-dependent initial value problems, whether we call the variable time or x, it doesn't really matter. But basically, I will specify my starting point, my value of a function at some starting point, and then after that, I will project what the values are on a certain interval. The example that we had in linear systems was a boundary value problem. I had a rule how temperature changes, and I actually had a set values in the boundaries. Okay. So those are so-called boundary value problems. I can discretize those as well, and in this case that we had, we actually arrived at a linear system. And one thing that we should recognize is that right now we are mostly focusing on first order, so all of the methods that we'll have are first order equations where I have only the derivative of the first order. We will actually, by the end of this lecture, we will actually see what happens if I have higher order. We are not looking into partial differential equations, though we could, and there are certain similarities, but one common one would be like a Laplace equation here for pressure. All right. So the simple initial value problem is given as dy dx is a function of both x and y. Okay? And the simplest attack or line of attack would be to start from that initial value that you have. Okay? And then from then on, sort of march through. And your next value is heuristically simply this old value plus some slope times the step h. And I'm not changing notation a little. H is not height of my reservoir anymore. It's simply the step size that I'm taking in this approach. So let me get a picture here. So let's say that I'm actually here, right? Xi, value of my function y at the point xi is this yi. Okay? So this is my starting point. This is actually the function y I'm looking for that I don't know. And the way I'm approaching this is saying, well, let me take a step size h, okay, and h away from my xi is xi plus 1. The value that I'm going to project the function will have at this point is this yi plus 1 is the value at this point, is my old value yi plus 1, so this is my old level, okay, plus this slope of this line times h. Okay? And that's a simple way to do things from this like imaginary triangle that I'm drawing here. And this slope is really derivative of the function y at this point. Okay? And according to my ordinary differential equation, I know what the derivative is. Dy dx is f of xy. This is given. Okay? So my simplest method, it's called Euler, says, yi plus 1 is yi plus this. This is my derivative at point xy of y times h. And that's it. So that is the simplest thing I can do. Okay? So it's not going to be the most or the best way to do. So technically, if my h is rather big, and we actually had a very similar situation that I showed you last time by hand, basically you could be more than 50% away. This is my true solution, and this is my projected value. But things do get better if I take smaller step h. Okay? So I'm just going to skip to I do want to finish the exercise before we comment on how close and what is the error that I'm making. But basically, this is what we started last time. I don't think we got to the programming part at all. We just really computed, so using this formula, okay, for the problem dy dx is f of xy. And this is my f of x. It's really function just of x, not of y, but it's a simple example where I can find, by simple integration, I can find analytical solution, so I can check how well I'm doing. And for h is equal to 0.5, I would simply start from x1, y1, as y of 0 is 1, so there are 0 and 1. So to get next value, my y2, according to the formula, is y1 plus f of x1 y1 times h. And when I do that, it's 5.25, and I think we computed last time that the actual value is 3.21. So I'm pretty much off because my step size is rather large. The whole idea, though, is that as my step size improves, so this is the step size of 0.5, if I actually do 0.1, I'm going to get much closer to this analytical solution. So pull out your computers. I want you to program this. So I want you to program both, plot this analytical solution and find solution using Euler's method, okay, on this interval 0 and 4. And essentially, you want h, this start of the interval, which is here 0, I'm going to call it x1, y1, which is your initial value, 1 in this case, and interval end, which in this case is 4, okay? Those should be inputs to the function. So I want you to do a function, okay? And you should spit out or give back x and y values on the interval. So essentially, just to start you off, what I want is function, okay, xy is Euler method, and your x1, y1, h, and xn are input values. And I'm going to immediately give myself a comment here that will tell me what those are. So x1, y1 are initial values of y of x1 is y1. Okay. H is step size, and xn is interval end. So basically, my solution solving the problem on interval x1, xn. So then you and I will walk around and help you do this. Yes. Oh, sure. That. So I'm going to try to squeeze both. So this is the assignment part. Is this visible enough? And of course, once you're done with this problem, I want you to compare the solutions for different h, which is why it's useful to have a function so you can just execute it as many times as you need for different h. And technically what you need to get is that plot that I put on the next slide. I'm going to stop the video since it's a lot of silence.